Good morning, everybody. We should get going. We have a fabulous session coming up. And my name is Stefano Bertozzi. I'm the Dean of the Public Health School across the Bay. And it's my pleasure to have co-organized this session with Michelle Berry at Stanford, and we're going to trade off some of the introductions. And we've got a fabulous lineup for you of folks who are both doing cutting-edge stuff and know the rest of what's happening in cutting-edge stuff and are going to share some of that. In bioengineering and biophysics, we're going to hear from Manu Prakash at Stanford. We're going to hear about robotics and diagnostics from Dan Fletcher. Who's at Berkeley. We're going to hear from Amy Batson, who's at PATH, the Program for Appropriate Technologies in Health. She's going to kick us off today with diagnostics, drugs, and vaccines. And then we're going to round it out with Carlos Bustamante from Stanford talking about big data and precision medicine. This is a session which I hope will give you a glimpse into not only the exciting things that are happening in each of their labs and organizations, but also on what's happening in their fields in the rest of this space. And then we're going to finish that up with a moderated discussion where we'll all come up and speak together. So I'd like to ask, our panelists are not going to sit here because they want to watch the presentations, but I'd like to have Amy come up, if she would. She's going to kick us off. Amy's got a very interesting and history. She's worked for lots of organizations. She's most recently at PATH, as I mentioned. She's going to discuss innovations with high potential for achieving the SDGs, taking examples from PATH's Innovation Countdown, and we'll give examples of upstream and midstream innovations with an emphasis on the importance of considering downstream issues when doing upstream development. Amy has worked at the World Bank. She's worked at the USAID. She was recruited out to Seattle, and she's been doing a lot of interesting stuff at PATH, overseeing their entire portfolio, working very closely with Steve Davis. So Amy, to kick it off, please give her a hand if you would.
Last year, world leaders united around the new global goals, the Sustainable Development Goals. And these goals will determine the global community's shared priorities over the next 15 years, from now till 2030. In the health arena, we set some really ambitious health targets, moving from just the control and the improvement of women and children's health to ending preventable maternal, newborn, and child health. Moving from addressing killing communicable diseases to ending them as public health scourges. We all know that we can only achieve these ambitious targets with new innovations in the technologies and in the approaches that we bring to these healthcare interventions. These new solutions are not only about improving the effectiveness compared to current standards of care. These new solutions also have to be about improving the affordability and the accessibility compared to the current standards. In the low resource settings where most of the world's population lives, these innovations have to be financially and programmatically sustainable to allow families, communities, and countries themselves to continue to use them to transform their own health and economic prospects. One of the big lessons learned, though, when we looked back at the Millennium Development Goals, these were the global goals that were set between 2000 and 2015, is that having a global goal is a tremendous opportunity because it galvanizes attention, resources, and accountability towards achieving them across the world. But frankly, the world didn't pay much attention to the global goals until the last 5 to 7 years, if I'm being generous. And it was at that point when they were monitoring and seeing where were their gaps, where were things not working, where were there countries that were not able to achieve the goal, and trying to understand why, that there became a little bit more interest in, oh gosh, what are the innovations that could really help fill these gaps, that could fuel the change? And at that point in the process, with only 6 years left, it was really too late to expect to see some of the best innovations in the world scrambled through the pipeline, introduced into countries and scaled up. So the government of Norway came to path to say, well, what about if we started at the very beginning of the SDGs? Let's start to identify what world experts think of as some of the innovations that could have the greatest potential to accelerate progress. And let's do it before we even launch the SDG goals. So the Innovation Countdown 2030 was born. The Gates Foundation and the US government joined in with Norway. And the goal was about identifying innovations wherever they're occurring. And it was also about making sure that we're breaking down some of the silos that separate those opportunities, those intersections where true innovation occurs, and making sure that some of the ideas that were coming forward were put forward in a way that made them more compelling and accessible, not only to the health techno-wonks who read this stuff all the time, but cross-disciplinary, cross-sectorally, and in fact spanning the various stakeholders who are absolutely critical to ensure that a great hot new idea at the science end translates into impact around the world, and particularly that's some of the finance and policy community. So the IC 2030 was all about let's rethink what's possible, and let's do it by asking around the world what are those kind of cool solutions, those potential game changers, and let's try and then catalyze more investment. Here you can see the way we started to approach it was first by crowdsourcing ideas. So not just going to the same old suspects who have brilliant ideas, but opening it up. And within a very short period of time that we had allowed in this project, we had over 500 innovations from 50 countries, with over a third coming from low and middle income entrepreneurs. We did a qualitative analysis that was validated in the community to then start that down selection process from 500 to 175, and then started to pull together the expert panels from around the world again to be using Delphi process to be further down selecting from 175 to 60, and then an interdisciplinary panel to go from 60 to 30. Importantly, we started bringing in some quantitative analysis to ensure what is the social impact across some of these different ideas, and do it in a way that made those estimates comparable. So consistent methodology, consistent sources of data, comparability, which is another important lesson learned. So what did we find? Well, a couple areas of learning. One is there were about 1 in 5 of the innovations were cross-cutting in nature. So they address multiple disease endpoints. And in fact, the global community is really bad at valuing innovations that have multiple endpoints, because we tend to value them within the communities themselves. So the TB community looks at innovations and says, what's the value to me and my TB goals? The immunization community looks at it and says, what's the value to me and my immunization goals? When you have innovations that actually address all of them, they tend to get under, the value of them gets underrepresented. Second is we saw that the experts were given a date, the 2030 goals. So it's a 15-year runway. It's still a pretty long runway, and yet there's still a bias towards some of those middle or late stage innovations, in part because they fit into the world framework that the experts have, and in part because there's more data. So less of a risk. So what I'm going to show you now are innovations both that made it into the 30, but also that were earlier in that process, in that 175, that may be a little bit more disruptive. So the first one around novel vaccine and drug deliveries. And we all know that immunization has been one of the huge game changers in public health, and has been one of the biggest drivers towards the reduction in under 5 mortality. However, 1 in 5 children still are not being reached with these life-saving vaccines. So one of the big questions for the community is, how can we increase coverage? How can we reach that 1 in 5 child? And so a lot of work going on around alternative formulations and delivery systems, including microarray patches, implants, fast-dissolving tablets, and inserts. So looking at the dissolvable or hydrogel microarray patches, very cool technology. What's the value of it to the world? It would reduce the risk of needle stick injuries and eliminate improper needle reuse. And just yesterday, I was hearing from colleagues working on Hep B and Hep C how needle stick and misuse of needles is still one of the primary forms of transmission for some of those bloodborne diseases. It has the potential for self-administration. So that would result in improved access, being able to slap on a patch as opposed to having to go to a clinic to get an injection. And it would improve the temperature stability of many of these products, and so enable the use of these products beyond the constraints of the cold chain. So an example, PATH is working with a number of collaborators, most notably the Emory University and the Georgia Institute of Technology, around exploring self-application and how does it change the demand paradigm and the supply paradigm of increasing access. Many others working on this: GSK, Queen's University, University of Queensland, WHO, 3M, variety of players. Very hot area. Second, innovations with a nose can expedite diagnosis. There's an estimated 9 million cases of TB in around 2014. 1/3 of those are undiagnosed. TB is particularly difficult to diagnose, particularly when there's a co-infection with HIV. And yet, it's one of the biggest killers in the world. It's also, there's estimates that in dense urban areas, an undiagnosed TB carrier can infect 10 other people in a year. So a low-cost rapid screening test would have a tremendous benefit. A group in Tanzania, APOPO, has had identified that TB-infected sputum has a smell. And so they've been using giant African pouched rats to diagnose TB. The rats are trained via stimulus discrimination tasks to detect TB by sniffing human sputum samples. And each rat can test hundreds of samples a day at literally peanuts. So now at this point, the test is still not sensitive enough for all the needs, and the method still does require a laboratory and maintaining training of rats. However, what's exciting is that by identifying that there is a unique smell to the TB sputum, other companies, at least 5 other countries, have started working on an electronic nose. So the idea of then how can we test for TB through a simple breath analysis, such as like blowing into an easy-to-carry machine with no sputum samples required. The challenge around these e-noses is sensitivity, but their simplicity, the speed, it's estimated they take about 5 minutes, and their relative low cost would be a real game changer in the TB field. And one company working on this is one group working on it is the International Center for Genetic Engineering and Biotechnology in India, and their electronic nose. Another major issue is around other types of diagnostics that could enable more prompt and accurate treatment, and in particular, the whole issue of nucleic acid amplification testing. The goal is to have NATs type of testings be more sensitive, more rapidly getting to diagnosis, and in simpler methodologies to enable use at lower levels of the system. You have groups like ALAIR in the US and CFEED in the US who are, with ALAIR, looking at cartridge-based assays for TB with a new and robotically manufactured low-cost molecular test platform that would be designed for use in lower-level labs and peripheral clinics. And with CFEED, they have the EXPERT, that's the automated cartridge-based nucleic amplification assay for detection of TB. Using sputum samples, taking about 2 hours, and in principle can be used at the district-level facilities. However, even these examples are finding are too complex and too expensive for the worldwide rollout that one wants to achieve. Here, PATH is working with, on NINA, or non-instrumented nucleic acid amplification types of test, which would be simple, inexpensive point-of-care platforms that would not require electricity, or advanced laboratory training or equipment. However, this platform technology actually requires a really collaborative effort of innovators to also be having other innovators who are able to develop the sample preparation methods and the right nucleic acid amplification assay reagents that could be used in the field. And it's that combination of this type of piece of equipment that could actually hold the sample and heat up without electricity to the right temperatures with these other pieces that are absolutely critical to make this type of thing work. The big comparator is cost. Whereas PCR lab sampling costs about $20, NINA is estimated that it would cost about 2 cents per sample. Other forms of diagnostics that are going on that are pretty exciting are around preeclampsia. And we know the risk of a pregnant woman dying from preeclampsia in developing countries is 300 times greater than we see in developed countries such as the US. The reason for the high mortality rate is that many deaths are still occurring outside of the reach of tertiary centers of care, and women are not being identified as being at risk of preeclampsia early enough in the process. However, what's particularly interesting here is that there are a lot of groups doing some very cool work around new, better point-of-care diagnostics for preeclampsia. However, the impact of those tests will be extremely limited unless there is equal work going on around improving treatment. And one of the things we saw with our IC 2030 work is while we got a lot of ideas on the diagnostic, there didn't seem to be a lot going on around improving that treatment. But some of the interesting ideas would be, for example, from the Research Institute of Nationwide Children's Hospital in the US, where they have the Congo red dot test. They've identified, where we know preeclampsia, women with preeclampsia have high levels of misfolded proteins in their urine. And so it's a low-cost, paper-based diagnostic and clinical prognostic tool to be able to quantify these proteins and identify preeclampsia. And what's really cool is it's just using a simple dye. Other groups are working on different ways of recognizing it. You have UBC, University of Michigan, Convergent Engineering looking at blood pressure measurement and arterial conditions as ways to predict. And you have groups of PATH looking at urine-based proteinuria screening types of tools. However, one last one I wanted to highlight is at the end of the day, what's hot, what defines hot, is not only all about the science. It's about what can actually have impact. And sometimes looking at old knowledge and old science in new ways can be incredibly exciting. And this is what frugal innovation starts to be all about. How do we turn R&D on its head to be looking at it from what do we have most available, what is going to be most affordable, and what can be reaching most people in the world with these innovations. So chlorine has been used to treat water and prevent infection for nearly 100 years. This is not hot new science. And it has become the gold standard for the developed world. Yet, around the world, billions of people still drink contaminated water. So, one solution is Zimba, which is an automated batch chlorinator which sanitizes water through adding chlorine at small-scale community-level treatments. Zimba was developed by the D-Labs IDIN program in India in collaboration with MIT. And it is fitted directly to a hand pump or community tap that automatically chlorinates water to a safe concentration without electricity and without moving parts, some of the biggest problems that we've had in water chlorination systems to date. It treats 8,000 liters of water between refills of the chlorine dispenser. What was exciting about this particular innovation is that of everything we looked at when we quantified the social impact, this Zimba treatment was the only one that had a net cost savings. So not only would it prevent 1.2 million deaths over the next 15 years, it could do so and save money for the community because it would also prevent so many cases and sort of treatment that follows around diarrheal and other waterborne diseases. So, in conclusion, when you're driving something from that hot new idea into what really has impact, you have to be looking at that endpoint. What are the kind of characteristics, the issues that are going to be necessary for this great idea to actually be introduced and scaled up in an affordable and effective way into existing programs? Also, the identification of that hot new idea and getting to that proof of concept is just the start of the journey. It's all about that tough stuff in the middle, about how do you navigate, how do you do the user-centered design and the hurdles to acceptance, and so forth, to ultimately ensure that it translates into real impact. So with that, I'd like to close, and if you're interested in seeing more of the types of innovations coming on from around the world in the IC 2030 count, it's available online. Thank you.
I'd like to introduce our next speaker, Manu Prakash. Manu is in the Department of Bioengineering at Stanford University, where he leads a curiosity-driven research group working in the field of physical biology. His research approach brings together experimental and theoretical techniques from soft condensed matter physics, fluid dynamics, theories of computation and unconventional micro and nano fabrication, to open problems in biology. Along the way of that very sophisticated sentence, the Prakash Lab actually invents very novel technologies within a global health context in extremely resource-poor settings, and which is all very nicely said in a great New Yorker profile on Manu a couple of weeks ago. Manu.
Is there a timer somewhere, or you're gonna 5-minute mark? Yeah, I have a tendency to go on. Not good. I'm gonna try to give a much more informal talk, and we'll try to see how far we can go in terms of the types of things I wanted to cover. I'll briefly end up talking about essentially surprises, surprises in technology that lead to some of these innovations. And then I'll briefly talk a little bit about what actually our lab does. I got some things with me, so maybe at the end of the talk, after the session, we can actually talk about solutions more directly and do some demos. So just to begin, my name is Manu. I work at Stanford, and I think to me, what is hot in technology and global health are people. I think, just when I think about the immense interest in global health from interdisciplinary departments, just in my own lab, there are people all the way from biochemistry to applied physics to molecular sciences that are truly excited and interested about taking tools and technologies, both designing them, but also taking them out to the field. So to me, that people connection is something that's really new that's starting to happen, where a very broad skill set is joining on board. And that's the personal case for me. I'm trained as an applied physicist, but I think about these things deeply. One thing that I just wanted to mention is a project, Foldscope, that's been started. We've just started an entity outside Stanford to scale one of the projects. So I'm one of the co-founders of that. I just want to mention that. Okay, so I have to start with Arthur C. Clarke. Any sufficiently advanced technology is distinguishable from magic. And when I think about technologies that truly scale, this sense of magic, I mean, this was very clear in Amy's thought process, is that really gets preserved in some sense. And when you start thinking about this and ask yourself, this week, what was the magic that I saw? I saw the Falcon land. I would have never imagined in my lifetime, and then suddenly you see it and say, okay, that's doable. Let's move on. And it really changes this paradigm of, I think, anticipating what is coming in technology is very hard, because the combinations of the way things come along give rise to human endeavors and feats that are really far away. So one of the things that we have to think a little bit about is, just because there is a solution doesn't mean that solution scales. So flip that around and think a lot about scaling from the very beginning. And that's something that's my favor of how I think about it. Because in the end, it's still true that 1 billion kids live in poverty around the world, and any of these solutions and any of these incredible ideas get at least us as technologists very excited, but they don't push forward. So for me, one of the factors of how I chose a few things that I'll highlight are just focused on surprises, and I do feel there is a potential of scale up at a massive scale. Why do frugal science? This is one comment that I want to make before I start, which is healthcare is very important, but the pillars of a developing society, both research and education, are as important. So in some of our own work and just all along, we've actually seen that the tools for frugal science will have even a larger impact when each one of these three things come together. These are some pictures from our trip of a hospital in Ghana and a field researcher working on mosquitoes in Tanzania and a school in Uganda, and you can see the striking differences in all aspects. So it's very crucial to not have these tools that were initially even developed for healthcare to actually percolate in other parts of the system. Okay, so let me tell you about a few things that I find really surprising. Laser pointer. Everybody's played with a laser pointer. I have it right here, and of course, now when I need it, my frugal technology doesn't work. Oh, sorry. No, it does work. Okay, you've all seen a laser pointer. Now what I want you to do is to pay close attention to the blurry stuff that you're seeing when that laser hits. So you see the big spot? but you see a little blur around it. That's called a speckle pattern in physics. The fact that when the laser hit that material, it got reflected so many times with the particles, it created a specific pattern. And just this week, this paper is not even out yet, it's on arXiv, a group actually reported that just shining a laser pointer on food and food products, if they are contaminated versus uncontaminated, have a signature that you can detect. The only technology here is just a single laser pointer, and then you are looking at what speckle pattern it forms. And here, for example, is the speckle pattern on something in which there were no living bacteria. This is an example of a bacillus and E. coli, and what you're seeing is that the speckle pattern dynamically changes. Why? Because life is alive and it moves, and it changes these millions of scattering reflections that will happen. And it's a completely different way of thinking about diagnostics from a point of view. And when I see ideas like this, it's almost to a point where it was very hard to predict, and suddenly it's just a fact. And now the goal is, how do you actually take them forward? I'll give another example, which is one of my favorites. And I have to do a little demo here. How many of you have played with Scotch tape? So you've heard this sound. I couldn't get my Scotch tape, so it's a little bit, I'm cheating a little bit. But I want you to hear this sound. That sharp shriek that happens, and with Scotch tape, it's even sharper. If I'm to tell you that that actually produces X-rays, it's a little bit mind-boggling when you think about it. A group of Russian physicists discovered this in the 60s, and a group in UCLA actually again rediscovered in the 2008. And they demonstrated that it has an intensity that you can actually generate an X-ray. And completely just, I mean, I don't even have words for thinking about how things will fold. And this is frugal science to me in its true sense, because actually the paper admits that we don't know how it works. And it's still a scientific challenge. But fast forward, this was 2008. Now there is actually a company that makes a handheld X-ray source that is the most robust source that's out there. And here is a challenge that I'm going to throw at frugal science, which is this could completely revolutionize low-cost X-rays, completely portable X-rays for all kinds of accidents and road accidents that happen around the world. But there still has to be a market incentive for that entity to be getting into this market, which is very hard to penetrate. So a technology exists at this point, but right now their focus has been on the short term, which is to use it in analysis locally. But frankly, this entire field could open up if we really think very differently about X-ray sources. I'm going to give another example of something that we've been doing in the lab, which is DNA origami. This is how somebody was explaining DNA origami to the president. And I did not sketch that after I saw that. It was an accident that I saw that, and I'd already made that sketch. But the idea is you take a long piece of DNA and you fold it together. And in 2006, a friend of mine at Caltech invented this technique called DNA origami, where you could make any possible shape at nanometer scales by just folding DNA. And at that time, people said, what is it good for? And he said, look, you can make smiley faces. 100 nanometers. It is the most advanced technology from a context of making stuff at this small scale. And he quoted to me that I made 100 billion smiley faces for a couple of dollars, the most happiness in the world. And fast forward, Abe Anderson's group, who we're collaborating with, actually took this idea seriously to completely question how we make molecular sensors. So he took the same DNA origami approach, but now he's actually putting FRET sensors on them to a point where one single molecule that was floating around, unlike PCR in which you have to amplify, and all kinds of errors come about, here, one single time, it's like a book. And if this thing opens up, suddenly hundreds of molecules will light up, and if it's closed, hundreds of them. So it's optical amplification done using molecular techniques. And now they're starting to think about applying this in non-instrumented tests for diagnostics. Completely different type of a sensor. How much time do I have? Okay. I think everybody has heard about CRISPR-Cas. I was going to mention a little bit about it, but let me come back to it in the very end. Another incredible technology that just came out of the middle of nowhere, and now everything is about to change, and we just have to embrace and get ready for it and have regulations in place to really be able to actually deliver this. This is a technology that allows you to drive genes, especially lethal genes in populations, to completely annihilate a species from the planet. Very scary stuff, but maybe it's time to think about it. So let me just tell you one or two examples, but I'll come back to that comment. This is work from our own lab. We spend a lot of time out in the field, and I think as a technologist, this is the first thing that I learned. I'll never be able to find the right sets of solutions if I don't go out to the field. And I was in Nigeria sometime, and I met this 30-year-old man who'd been training people to do diagnostics for 30 years, a 60-year-old man. And he said, bring me tools and technologies can do diagnostics under a tree. And just personally for me, that was the motivation. And the way I think about technologies that I touch, I'm thinking about those constraints of what can I do under a tree. And no power, no regular infrastructure, broad group of people using it, but still you want to get specific answers. And the types of users that I think about, this is another man that we met who described me his lab. He has 4 years of training in medical technologies and healthcare at a university, knows more microbiology than me, gets placed out in the field, and this is his lab, which is, he told me, the beds when the patients are not there is my lab. So the types of tools that I personally think about are the tools that would go into the hands of people like him. We've been working on our own NINA. I didn't know that term until now, so I'll start using that. We call this punch card microfluidics, a way to get rid of all the pumps and valves and all that electrical infrastructure that's associated with all these automated molecular diagnostics platform. It's inspired from a music box. So your assay or your protocol is a card that you read, and those little holes are not just random holes. They actually specify the exact protocol. There is a hand crank. You crank it at any rate. The card moves at a specific speed, and you can do very broadly any range of molecular assays. In terms of thinking about pipetting, this is a 30-fold pipetter that's completely manual in some sense, but then allows you to do a large number of reactions simultaneously. And we're applying this platform essentially for malaria, and one of the things we're looking at is RPA, but also these types of sensors that I talked about, which would be incredibly powerful if you can use them precisely. So this is a thread that we're pursuing. We have done some work in environmental pollution with this, and now we're targeting malaria. Another example from the lab that's a little bit more well-known, so I'll spend less time on it, is we've been making microscopes out of flat sheets of paper. Somebody made that cartoon because that represents the cost. It costs us $1 to make, and we can do anywhere of the range of 700 nanometer resolution imaging at a price point of $1. Another way somebody compared it is that's the microscope. We call it Foldscope. That's a regular microscope, and that's a banana for scale. One of the things about something like this as a project was a slightly different approach that we took. So it takes 5 minutes. I have one, and a few actually, that I can show and share with people. One of the approaches that we took with this is, how does community react when you bring up a technology? Because we don't know all the answers. We don't know where it should be used, so we decided to share it. There are many ways to use it. You can couple it to a cell phone. You can project images, and you can directly image. You can see many types of pathogens. We have done clinical work on these pathogens that I'm not going to mention. But I want to mention something that we did differently, which is it dawned on us that why not share this technology? And in the lab, we made 50,000 of these. And if you go tell your grad student tomorrow we're making 50,000 of these, he looks at you really funny. And that's what happened, but literally the lab turned into a manufacturing facility because we had a gut feeling that what people will be able to do with a broad accessible tool. We wanted to do that as an experiment. And till date, we've shipped 50,000 instruments around the world, 130 countries. Every single dot is hundreds of microscopes, all the way from Madagascar to Syria to Iran to Mongolia. And what's incredible is the types of examples that people come up with when they are thinking. There was a kid in Nigeria that came up with the way of using these microscopes to detect fake currency. You know, the fact that when you turn your $100 bill, they return it back at microscopic scale, you can detect it. There's another pharmacist who's using them to detect fake pharmaceutical drugs because the encapsulation process requires them to polymerize into these polymer capsules. And to me, the heartwarming story, this is a group in Tanzania that's exploring sanitation. So there is a big program that we're running, exploring if kids are taught germ theory from the very beginning, would there be health impact that they would just wash their hands? And one of the things that's happened is we are not driving it. We're providing the tools, but the community is driving it, which is the most fascinating thing in terms of thinking about this. This is an example of the instrument being introduced in Kaziranga, which is a biodiversity hotspot, but one of the most dangerous places to visit. And what you're looking at are essentially guards that kept their guns on the side and then learned and did microscopy because they're also trying to appreciate and understand the biodiversity that grows in these places. And I think to us, the best thing has been is taking these technologies to people who we didn't even think were the source for this technology to begin with and letting them drive applications that would come out of it. There is a large community. You can visit this website and thousands of explorations. So this is very organic, open science that happens beyond. And I could let this thing scroll for 10 minutes, but I'm going to stop. OK, how many minutes do I have? Am I out of time? OK, maybe I'll just end with this. We recently also did a clinical study of looking at an instrument like this, but slightly more structured for infectious diseases, looking at schistosomiasis and helminth infections. This is a microscope that's essentially the optics is the same, but it's designed as a projection scope. So there is no digital coupled entities to it, but you watch it. And we just studied, we're writing this up right now for diagnosis for helminth infections and schistosomiasis. I was going to talk about mosquitoes, but I am out of time. We, just as one single plug, we've just figured out in the lab how to use flip phones to detect species of mosquitoes that are flying around. All of you are very excited about Zika and many other things. It's incredibly important to understand ecology of mosquitoes. So this is, we're about to write this paper, so this will become available soon. But I'll end here and take questions later.
Told you guys this would be fun. So for our third speaker with more hair than I, we now have Dan Fletcher from Berkeley. He's the Chatterjee Professor of Bioengineering and Biophysics, chair of the Department of Bioengineering, where his lab investigates the biophysics of host pathogen interactions and develops diagnostic medical devices. He's received all kinds of awards, NSF, Tech Award, and designated Best of What's New by Popular Science, served as a White House Fellow, and has founded the medical device company called CellScope, an interest he shares with Manu. Dan.
All right. Thank you very much, Steph. It's a great pleasure to be here. So I will pick up where Manu left off and talk about innovations, but try and make the case for the use of digital technologies. OK, all right. So I think all of us have these and probably using them right now to pass the time as this session goes by. And these are very readily available, and thanks to everyone wanting them, using them, needing them in many cases, the cost of producing these have gone down and down and down. And I would suggest that when these were first introduced, that it would have been a bit crazy to predict that they would have spread throughout the world throughout regions where electricity is scarce, throughout regions where there isn't an AT&T store on the corner, but rather mobile phones have become such a part of the fabric of many places that we would never have expected. Maybe we can think about them as being a part of frugal science. So let me talk a little bit about what digital technologies, consumer technologies can enable us. And that's basically the concept of automation. That many of these devices do things automatically that in the past we would have had to have somebody or much more equipment to do. And so that could be in the form of recording a message. We no longer have a person that sits at a telegraph office and takes down what those dashes and dots mean. That's now been automated in various forms, and we now can transmit information in very robust ways. And it's that robustness that I think becomes really important when you try to apply technologies to healthcare or to areas of the world in which we need validity and veracity in our data. And so data quality is a recurring theme in what I'll show you coming up. Okay, so how can we use automation, the ability of digital technologies, to push high quality care to lower level health clinics? So let me start with a few examples. So this is a remarkable variation on a stethoscope. And this was actually produced by undergraduate students at UC Berkeley. And it is a Bluetooth-enabled stethoscope. And so basically it records, as you are listening to the heart, it records that information, connects it to an app, and then is able to either transmit that recording to somebody else for interpretation, or eventually may be able to participate in automatic identification of heart murmurs, of other indications of disease. So simply taking advantage of the technology that's already been cost reduced dramatically in our pockets, but applying it to an information stream that normally only a trained individual would be able to make use of, that's opening up, providing care to a much broader set of people. A related technology is an ECG. Being able to make electrical measurements of heart activity is something that in previous years would only be done in the hospital. But now, in developed countries, that's being done on an individual basis. You can now get a device that you can wear continuously, and it will report out how your heart is behaving. And what's more, it can give you an early warning that there is some sort of arrhythmia. And it can tell you, either you can ask it, you can make a measurement at one point, or you can have a continuous monitor and it can report. And that's an example of where software automation is looking at that signal and identifying, wait, something is anomalous here. And that capability now means that in a mobile phone-based system, the ability to monitor how the heart is behaving is something that's not just accessible in developed countries, but pushes that ability to interpret, to identify, to analyze to much lower level health situations. So a third example is an ultrasound. So an ultrasound system that is not the cart that you wheel into a patient's room that has lots of electronics associated with it to generate the ultrasound field, to interpret it, to handle the data and do the interpretation of it, produce an image. But rather, here's a device that's built by Philips Electronics that is able to plug directly into an iPad or a tablet computer and provide that real-time image of whatever's being investigated. So for maternal care, for surgeries, for other applications. And these technologies, the three I've just shown you, already exist. They're already being produced. And the point of how they can become used in developing regions comes back to the question of cost, of course, but market demand. How do we re-envision the clinical setting in a developing world setting that doesn't simply mimic what we do here, but is created to take advantage of the automated technologies that are being developed. Now, this area of automation and use of digital technologies is of great interest still in the academic world, and here are a few examples that I like. In Rice University, there's work being done on paper-based DNA amplification as well as identification of particular parasites. And that doesn't require any electronics as it's developed there. But you can imagine for interpretation purposes, if a phone is able to take an image of a lateral flow strip and to digitize it and quantify it, you have the added benefit of taking the user out of that interpretation step, but also you have a record that you can now begin to use in a variety of different ways. At Columbia University, another type of microfluidic system that's aimed at detecting samples within blood, both looking at hematocrit or hemoglobin content as well as antibodies. And then work from Boston University of taking something that's very standard in hospitals and making it very low cost, so you can get an automated readout of blood oxygen levels. Now, my own lab has been interested in this for a number of years, and I should admit that it didn't come from, initially at least, a desire to impact global health, but really because I hadn't yet come up with a project for my undergraduate class, and I needed to come up with something quickly, and I had noticed that phones started to have cameras on them. There was a time when no phone had a camera on it. In fact, you didn't have a phone in your pocket. It's hard to think back to those days, but there was a time. And I didn't have a camera on my phone, so I did get to borrow my sister's flip phone, which is pictured here. And it had a camera, and the challenge to the students was, can we build something that converts the image that's being taken by this phone into something that is being taken by a microscope? So rather than taking a big object and making it small onto the sensor, can we take a small object and make it big onto the sensor? And so they were successful in building a prototype that was initially quite large, and we've now been able to condense that. This is from a number of years ago. You can tell because this is a Nokia phone, which some of you may not even remember what Nokia is, but they made phones. And they had a whopping like 1.2 megapixel camera on it, and we were enthralled with all it could do. So these capabilities are only growing. I think there's a great opportunity for global health technologies to ride the wave of what consumers want out of their electronics. If you've seen the advertisements for the latest Samsung mobile phone, I think the tagline is something like, good things happen in the dark. And they are highlighting all of going to a club and wanting to take pictures of people celebrating, and as a result, they've developed this really low-light sensitive camera. Fabulous. Because you know what else is happening in the dark? A lot of molecular detection. Being able to capture fluorescent molecules, their activity, that is going to be tremendously moved forward by the fact that mobile phones have even more sensitive cameras. And so consumer demand is driving something that is benefiting the other side of the population. So we got excited about what mobile phones might be able to do after putting a few samples in front of them. We could see blood cells with sufficient detail to work out what types of cells they are. Possibly blood counting would be possible to do. The thing that got us most excited was the fact that fluorescence was possible. And that really is enabled by these low light cameras, that you're able to do detection of malaria parasites inside of red blood cells just with an acridine orange stain. With tuberculosis, and Oramino is able to detect, you're able to highlight where the bacterium is and capture images. But capturing these kinds of images is really only part of the challenge. If you want to detect or diagnose any of these diseases, WHO guidelines suggest you need to look at 100 high-power fields of view. And that means you've got to have someone who reliably goes to 100 different places and reliably interprets that. And there have been studies to show that that's not so reliable after all, especially depending on the number of slides that have been read and the skill and quality of the training. So is this a place where automation can, again, contribute? So let me give you an example from some recent work we've been doing on Loa Loa in Central and West Africa. This is a worm that I'd never heard of until I got a call from a colleague at NIH, Tom Nutman, describing a challenge. And the challenge was how to detect the number of Loa Loa in the blood, but to do that in a point-of-care setting and to do it quickly so it could be part of a mass drug administration program. Now, a little bit of background on why Loa Loa is an issue, and it has to do with onchocerciasis. So ivermectin treatment has been tremendously effective at reducing incidence of river blindness, but it was observed years ago that for some regions where they're co-endemic with Loa Loa, that you can have a serious adverse reaction when you give ivermectin and someone has a high load of Loa Loa microfilaria in the bloodstream. And that risk goes up with the number of Loa Loa. So it was thought that there's a safe level of microfilaria of Loa Loa that you can have and an unsafe level. And if you're above that level, then you need to not receive ivermectin. But that's only going to be about 2% of the population, and so how do you find that 2% efficiently and effectively and enable the other 98% to get the drug that they need? So as a result of the problem, delivery of ivermectin has been halted in a number of places. And so over a few years, we worked with teams in Cameroon and at NIH to develop a mobile phone device that we ended up completely automating. Our first attempt was one that was manual, and we found that the incidence of errors was quite significant. And so a way to make this as effective as possible and to limit the number of errors was to automate everything. And so this was the other extreme from the way I had been thinking about the whole reason to do mobile phone microscopy, was to make it so simple that people could use it in a number of different settings. But in specific cases, there may be an argument for total automation. So in this situation, we've got a device that communicates through Bluetooth with a little Arduino board that runs a motor and turns on a light. And basically, the system, with a compact set of lenses, is able to visualize worms. And what they do is actually visualize worm motion, not the worms themselves. So if you load a capillary with whole blood, so you don't have to do any treatment of the sample itself, you stick it into the device, and so you can see the little capillary sticking out of the right side of the box, and it operates like this. So you basically load it in, press a button, and the focusing is automatic. The sample is pulled in automatically, and a video is taken. And the video looks for disturbances in the red blood cells, and based on an analysis of that happens on the device, it gives a result. And so that happens in about 2 minutes. And so at the end of last year, we were able to build a number of these devices, work with partners in Cameroon on how to carry out an evaluation of these, and actually start to use these as a way of restarting mass drug administration programs. And so this has happened outside of Yaoundé, and it's been a wonderfully wonderful project to see whether automation can work. And there are a couple other places where automation, I think, can also play a role. Tuberculosis is another area where we're eager to work. But it's interesting to go back to one of the points made in the first talk, and that is the siloed nature of diagnostics. Even though the same exact type of device and automation can work and be useful for tuberculosis, for microscopy of TB, of Loa Loa, of malaria, of a range of other diseases, that's not the reward structure currently in place. And so we have worked on individual devices for individual diseases, and I don't think that's the most efficient way forward. So maybe we can talk about that at some point in the future. So I'll end just with thinking about the other areas in which automation may play a role, and here are a few different projects that we're engaged in right now that extend beyond health to include environmental monitoring as well as detection of food quality and the like. So I'll end there. Thank you.
Our next speaker is Carlos Bustamante, who's a professor of biomedical data science and genetics and chair of Stanford's new department in biomedical data science. His research focuses on human population genomics and global health, developing statistical and computational and genomic resources for enabling trans and multi-ethnic genome-wide associations. He is one of the principal investigators of the $25 million ClinGen project to build the country's national database on genetic variants. Carlos.
Thank you. First, I want to thank the organizers for the wonderful opportunity to be here with you today, telling you about some of our work. And it's great to see a couple of the themes that are common across the presentations. I figured that instead of showing a litany of potential things we could do, hold on, let me just get this thing up and going, I'd sort of do a deeper dive on where I'd hope we'd be able to go. Let me just, doesn't give you a lot of confidence that I know what I'm doing in this new department, right? But it's not a department of tech support, all right? All right. So in thinking about big data and personalized genomics, I figured we'd start with probably the biggest project that we as a society, or at least in the United States, are undertaking, the Precision Medicine Initiative. And here's Obama talking about PMI, which for those of you that didn't see last year's State of the Union address or haven't been keeping up with this, is essentially a giant effort to bring together electronic health record and some amounts of genome data so that we can mine these data to improve human health and well-being. And the wonderful talks that my colleagues gave today, just imagine in the same way you have all of the photos you've taken and the videos and geolocation on your phone, there is a world coming very soon where all of your electronic health record, all your personal wearables data, all of that's going to get integrated, and it's going to get integrated by the big boys and girls, right? So Google has a big effort on this, Microsoft has a big effort on this, Baidu, SAP, who we've worked with. So that world is coming. So let's give that as a given. We will live in a world where your electronic and personal health record and all of these wonderful diagnostics that are being developed will be linked just the same way your photos and videos and cat videos are all kind of linked together in one place for you, okay? So what are we going to do with that kind of data, and what are the kinds of questions that we can ask? Well, one of the big motivations for doing this is the sort of PCSK9 story. So how many of you have heard of PCSK9? Okay, great. So PCSK9 is the latest in a new generation of cholesterol-lowering drugs, which have been identified, and there's a tremendous enthusiasm in pharma for identifying such genes through large-scale genetic studies. And in particular, it began looking at families with hypercholesterolemia and finding that these families had overexpression of this gene called PCSK9, which is involved in sort of normal cholesterol transport. And it led to a very tantalizing hypothesis. If families with very high LDL, or so-called bad cholesterol, have overactive PCSK9, is it the case that perhaps people with naturally low levels of cholesterol might have low levels of PCSK9 or even non-functioning versions of PCSK9? So Helen Hobbs and colleagues began to look at so-called extremes of the distribution, and sure enough, when they looked at the very, very tail of the distribution, they found that people with loss of functions in PCSK9, those that had one copy that was defective, actually had about half the circulating LDL LDL levels. So these people could eat whatever they wanted, right? Go out for barbecue every day, eat all the fat you want, and your PCSK9, your LDL level was something like 90. Okay, which most of us would love to have, right? Furthermore, it is a pretty great way to get at causality, because you could ask, do the genes that predict your LDL level also predict adverse cardiac events? And that's exactly what's happened, right? And that's one of the very strong levels of evidence that LDL is causally linked to cardiovascular disease. The flip is also true. There are lots of studies that predict your HDL from your DNA, but don't have any link to cardiovascular outcome. And there are 5 drugs that have failed clinical trials because they've done a great job of raising your so-called good cholesterol, but at the end of the day, there's no real clinical efficacy. So what do we want to do? We want to mine the treasure trove of genetic data to identify more PCSK9s. The other kind of cool story that I'll end with, there's somebody who's a homozygote for PCSK9. The woman she's an aerobics instructor and has an LDL of like 25. Right? So now you know it's safe, right? This woman's been dosed since birth, has no PCSK9, and she's totally safe, right? And so now there are 5 drugs making monoclonal antibodies to PCSK9. Here's an example from what the NCI would like to do, namely tailor your cancer therapy to not only your genome, but what you see in your tumor. And this is wonderful. This is just so incredibly exciting, except for one small detail, which is that the vast majority of studies have only been done in populations of European descent. So 96% of the participants that have been involved in the kinds of studies that we are undertaking as a society to identify the next line of therapeutics based on genetics have been from populations of European descent. Is this a problem? Do we need to worry about this? I mean, this is a real scientific question. It could well be that the structure of human genetics is such that it's just okay to focus on one population, and what we'll learn in that one population will translate, and that, of course, Europeans are the logical ones to focus on. That could be a scientifically rational strategy, or there might be some value in broadening representation, and that's actually shockingly a novel idea, right? To go to Manusha's point, people are the disruptive technology here. So, I'm just going to set out some very simple questions. Why do we want to study diverse populations in clinical genomics? What's the potential scientific gain? 2, what have we learned when this has been done? I mean, there are some studies that have been done in other populations, and I didn't know, but Dr. Tapia is here, and the Slim Foundation's actually led the charge, and one of the shout-outs I have is to them. How do we properly design such studies, which is what a lot of my lab works on, and how do we think about modifying protocols and issues related to return of results to participants? And I also am going to make the radical point that ethnic diversity isn't the only kind of diversity that's relevant here. Socioeconomic diversity is probably really important, environmental diversity, all kinds of things. So let's just try to unpack that. And this is part of the charge. I wrote a paper in 2011 with Esteban Bouchard and others to really kind of move this agenda forward and argue that we are really doing ourselves and our patients and the world a disservice by only focusing largely on populations of European descent. Okay? And here's one example. Okay, this is the very well-known case of genetic variation in HLA and the response to abacavir. So if you happen to be HIV positive, you get your triple cocktail. One of the components of that triple cocktail is often a drug like abacavir. And if you happen to have this particular HLA allele and you get abacavir, you get really, really, really sick. Okay, the first time you get it. And my dad, who's in the audience, is an HIV doc, and we were just talking about them. I asked him, how often do you genotype your patients? And he goes, well, no, in the US it's standard of care, right? But what about in other parts of the world? And what are the general patterns that you see? And he was telling me, you tend to never see African Americans that carry this. And that makes sense. If you look at the global distribution, Yorubans, who are a West African tribal group, and similar to the ancestor of modern day African Americans, about 80% of the genome comes from Yoruban, but about 20% comes from Europeans. And in Europeans, for example, in US whites, you see it at about 5%. Now, but if you're practicing in India, well, 20% of the population carries this. Now it becomes extraordinarily relevant, and the second most common group from publicly available data are the Maasai in Kenya, right? And I'm a trained population geneticist. I trained people in population genetics, and I can tell you there's no magical first principles that tells you if you see something at high frequency in India, then the next most logical place to look is the Maasai, right? It's not like you're going to intuit that and say, oh, of course, right? Of course that's where it's going to be, right? There's just an empirical need to go out and catalog these genetic variants and genotype a ton of people. Furthermore, this is, a known genotype-phenotype reaction that is so well understood that many of us are arguing just put it in the frickin' EHR. You should get a big red flag that says genotype, genotype, genotype. Do not give somebody a back of ear if they've got this allele, okay? And that's being done with a bunch of variants. But how do we do that? How do we think about that problem? How do we go out in other populations and identify these kinds of associations? And then that's what a lot of our work on. I'll give you just one example from our own work, which I think illustrates why this might be the case. So this is, we got interested in blonde hair, right? It's very similar to Manu's work. Very simple question. Why do people have blonde hair in different parts of the world? It turns out there are two major populations that have blonde hair, Europeans and surprisingly Melanesians. It turns out there's a naturally occurring form of blonde hair in Melanesia. And this guy, Sean Niles, came to my lab to work on this. And I initially said, Sean, look at this kid's U.S. Serviceman's jacket. I can tell you the origins of blonde hair. It's some kind of Captain Cook allele that... But it turns out we were able to go in and do the study, and some of you know these are called genome-wide association studies, and this particular plot is a Manhattan plot. We like to call it our Dubai plot because there's only sort of one very, very big point of association, and it turns out to be at a gene called TERP1, which is very well studied, and it was it was fun to publish this in Science and say, look, this is a genetic basis of blonde hair in Europeans. But what's cool is that not only is this the basis of blonde hair in Melanesians, number one, this is a gene that's also the number one overexpressed gene in metastatic melanoma. So there's definitely a link to what skin pigmentation is related to, namely sun exposure and vitamin D metabolism and folate and all the links that we've known about for 50 to 60 years. So that might explain perhaps differences in incidence of disease. Secondly, this has been studied to death in other populations. So in fact, it is also the form of oculocutaneous albinism type 3, which was first described in a South African family. So this family has a different mutation in the same gene that is far more disruptive. That's why mom and dad are both carriers and the kiddos are homozygotes and albinos, and so it gives you sort of a sense into the potential medical genetics. Interestingly, we've worked on other model organisms, and you can use model organism biology to immediately understand and model the mutation. Furthermore, this is what we would call chemically induced blonde hair variation. But if you're European and blonde hair, you have a mutation in the OCA2 KIT ligand region. You don't carry this mutation. Okay? So here's blonde hair. You don't need to be a Stanford-trained dermatologist to phenotype blonde hair, right? You just need to be about 5 years old and ask, why do people in different parts of the world have blonde hair? You go out and you do the study, and you find out it's different. Why would we presuppose that diabetes has exactly the same genetic cause in all parts of the world? Why would we presuppose that heart disease has the exact same genetic cause in all parts of the world? And it's an empirical question. You've got to go out and do the study. And so, there is some population genetics that can help us here. Namely, the frequency of the mutation is directly related to how exchangeable it is. So when we talk about common genetic variation, a pair of European populations are essentially 100% exchangeable. A European and a Chinese population, or even a European and a West African population, are pretty exchangeable. So what you learn in one is likely to be true in the other. However, when we start talking about rare variants, mutations that occur that less than 1% in the population, these tend to be extraordinarily population private. However, the vast majority of genetic variation in the human genome falls into this category. It is extraordinarily rare. It's things you see in 1, 2, or 3 people. It is mutations you see in families. They don't contribute very much to population level risk because they're individual mutations. But as Tolstoy told us in Anna Karenina, every unhappy family is unhappy in its own way. Right? So as we start looking at individual cases, as we start looking at different parts of the world, we are going to expect to find a ton of genetic heterogeneity, and we're doing a tremendous disservice by only focusing on one part of the world. Okay? And now this has changed, and this is that wonderful paper that I was mentioning from the Sigma folks that identified a new mutation in a new gene that has to do with diabetes in Mexico. Something like 25% of the population carries it. It's extraordinarily rare outside of Mexico, right? This is the blonde hair gene that we found, and a list of others, right? And so now NIH has gotten serious about it, and we've been tasked with helping design the next generation of tools to do this. Our work from our lab has been in building the network of collaborators throughout the globe to do this. And then our work with the NIH has been to develop a reagent called the Illumina Mega Array that has 1.7 million markers on it. It was specifically designed for trans and multi-ethnic work, specifically designed within the United States to target a cohort of Hispanics and African Americans and Pacific Islanders and South Asians that we'd recruited. And for about $55 a sample, we can genotype 1.7 million markers and allow these populations to really be brought into the fold. We've got the largest multi and trans-ethnic study in the US, about 50,000 participants that are being brought into this. Here's just some of the variation that's on there. Part of this was done in collaboration with a project on African genomic variation. Part of it was done in collaboration with ClinGen to put variants of unknown significance on there and clinically relevant content. And I think this is the last slide, and you don't need to worry about the details. The point of this slide is to say that the algorithm we chose to use to identify variants to put on the array was specifically designed to enable trans and multi-ethnic mapping. So it matters. It matters that you're wanting to embrace diversity in your study because you will make different design decisions in how the tool is designed, right? If you wanted to go deep in a European population, you wouldn't use our design. But if you want to kind of be able to look across populations, find things that may be common and unique to populations, and then genotype everything in a global context, then you're better off using our array. Right? And so that was part of the goal, being able to demonstrate that, hey, there isn't one solution. There are lots of different optimization solutions. It matters what your objective function is. And our objective function is to do trans and multi-ethnic studies because the data just isn't out there. We don't know the relevance of the vast majority of the variants we've already implicated in clinical care in populations outside of Europe. And I just view that as catastrophic, right? If we're going to be putting things out there that are based on the next generation of drugs, the next generation of therapies, and we haven't even taken the care to figure out how relevant are adverse reactions in other parts of the world, then by definition, we are contributing to the broadening of health disparities. You know, and that should not be. This is the kind of stuff that's very easy and standard to do, so we have to do it. All right, so lessons learned so far. Common variants are rare and shared. Rare variants are common and largely population private. That means we need to enable trans and multi-ethnic studies. When GWAS studies have been done in different populations, they've yielded new biology, both novel variants at previously associated loci. So now we know of a bunch of mutations in LDLR, the LDL receptor, and in PCSK9 that are relevant for some populations and not others, similar to CFTR and cystic fibrosis, right? The delta 508 allele that predisposes to the number 1 Mendelian recessive is at high frequency in Europeans. That doesn't mean that you don't have cystic fibrosis in other populations. You got to go out and genotype them and look for them, and health screening needs to happen. And then secondly, you find new genes, right? It's not just about cataloging alleles, it's about finding new genes, both our TERP1 for blonde hair, the Sigma one for SLC16A11, and it's just a floodgates that we're now opening. The NIH is beginning to develop these reagents, but they need far more, and so we've been hammering on PMI. Every time I'm on a PMI call, I'm like, you know, the diversity chair. What about different populations? What about different populations? What about different populations? And we've now been able to move that agenda forward and haven't gotten totally thrown out of NIH halls yet, so that's a good thing. And then the challenge is, I think, you know, to a room of global health folks, epidemiology is important. Of course it is. So we need a ton of work on study design. We need to think about interpretation, right? As we go out and sequence a bunch of people at BRCA1 and 2, if you're a Utah a white woman, then your variance of unknown significant rate's like 2%. But if you are, from Mumbai, your variance of unknown significance is like 20%. Is that cool? Are we all right with that? Because I'm not all right with that. I think we need to do far better in sharing data to enable those barriers. And inclusion doesn't just mean ethnic diversity, right? How do people take clinical genetic test results and make decisions? Is it a decision that a poor person would make about getting a double mastectomy different than somebody who has, extraordinary wealth and can get all the reconstructive surgery they want and gets covered, right? Well, that's an important question that we need to address and think about as a society. And lastly, this is a whole session on new technologies. We all love new technologies. I love new toys, right? Everyone does. But new technologies risk broadening health disparities. So if from the outset we're not thinking about health disparities, then letting things run their natural course is just going to create a far new set of problems than are necessarily getting solved. So with that, I want to end and thank you and take any questions folks might have.
I'm going to ask the speakers to come up, and we're going to open it up to Q&A from the audience. And we have a microphone in the middle, so please come forward. And I guess we'll take from the audience. Go ahead.
Thank you very much for very interesting presentations from all of you. My name is Job Mugire. I'm a medical doctor from Kenya, but I'm currently taking a master's in global health in the UK. My question is, looking at so much of what we have seen come into the market, and based on where I practice medicine, I am concerned, always concerned whenever I see new technology. For example, when I heard about this device for ultrasound that I can carry with my smartphone into a clinic in a rural area and be able to serve with it. And I was only disappointed to learn that it's not available in Africa. And even in the US where it's available, it's only available as a rental product. You have to keep paying rent for it every year. I don't think there can be anything as frustrating as to have a solution available and be subject to similar situation as intellectual property limitations which hindered the availability of drugs for HIV/AIDS. What efforts should be made to make sure some of these very interesting and practical solutions we come up with do not remain inaccessible to the people whom they need to serve? Because nothing can be more shameful than to have a solution available in 2016, available in the market, but only accessible to the people who need it in 2076. Thank you.
I'm going to ask Amy to answer that, but I would also have to add that there's tremendous disparities in access even in the United States. So, Amy.
It's an extremely good question, and it's that whole issue of you can have some great stuff, but if it's actually not reaching the people where it can have an impact, what's the value? I think there's a couple important pieces to addressing it. One is it's the voice of the country. So making sure that policymakers in countries are assessing what's in the landscape, what are these innovations that are coming available, and which ones are going to be important to address their health needs is extremely important. And that voice is not very loud right now. So we need to do a better job, and you need to do a better job of our figuring out how do we elevate that voice, how do we get the data to support it. The second piece is with that data starts to come the market solutions. So the type of work around the market dynamics, how do we ensure that there's adequate supply, that there could be guarantees to mass production of this so that we could get more supply out there, we could overall drive down the prices, we could look at different types of arrangements around licensing or procurement or whatever may be the right solution for that particular product market can start to happen. But it takes the attention that this is something you want for then the world to start trying to gravitate around what are the market solutions that we can come up with.
Next.
Okay, thank you very much for a very exciting, brain-tingling session. I just want to follow up on what my colleague said. My name is Joel Igu. I'm a Nigerian medical doctor. He has addressed the issue of a lack of access. I would like to draw the spotlight to an issue in that continuum. What about the equipment that is currently on the ground? And when new equipment is deployed, what are the strategies to ensure that they can actually be used? In Nigeria, there are a lot of machines that use reagents. There are a lot of currently existing machines that are not being used but are functional because there are no reagents to run them. These reagents cannot be purchased. There are a lot of equipment that have very minor issues that cannot be fixed in Nigeria, but this renders this machine completely useless. So you have a bunch of very expensive machines just sitting idles in clinics where they are not being used at all, and they cannot be used at all because they cannot be maintained and they cannot be upgraded. I believe the USAID has a policy for using only American-made instruments or equipment, perhaps, and this really causes a problem because when they pull out of any project, all the equipment gets left behind. Any other NGO just brings its own bunch of equipment, which it will also leave behind, and then you just have a whole bunch of equipment doing nothing in these facilities. So that's what I want to know. Thanks.
Manu?
So I was going to make a quick comment on both these factors that you brought up. I mean, I think as technologists and as people in the early part of the chain, one of the things that worries me is always the fact that there is a point of time when scale-up, I mean, we make scalable technologies, but then the scale-up has to happen. And we have to be very careful because there are lots of markets, there is a lot of market pull in which then technologies get like, I mean, the classic example was the X-ray machine that I was talking about. The capital that was raised around it is really around metal detection, and although it's an incredible technology, the venture capital that supported the next stage of the work only narrowed it down. So it only, not only just the fact that the ultrasound machine is not available, there are hundreds of other technologies that really are actually scalable, but that next step doesn't go through in the way we would like the market to move. And the other comment I was going to just make is, I think this is why the point that you raised is, you know, science, research, and healthcare are all integrated. Is the fact that the medical school students who are engaged in these things, this is the most exciting thing for our graduate students, is to open up the machine that they've been building. So I think it is a mistake to think about that market solutions will come when early on we don't actually have a pipeline where the basics of the solutions are not available. If people don't truly understand microscopy from the fundamentals, then even if there is an incredible machine sitting there, after some point of time, it'll turn into a black box. So I think there is a disparity in us thinking about this.
I just want to echo that it's all about the incentive structure, right? So, you know, you're out in Silicon Valley, everything out here is, you know, it's going to be a technology, right? Every solution here is going to be a technology solution because, you know, when you got a hammer, everything looks like a nail, okay? And the way you fund those technology solutions is venture capital who are looking for products that have certain business plans. And the business plan that works the most and the best is a plan where you have a continual need for reagents, where you make all your money. So most sequencing companies make, you know, a ton of their money just on the reagents. They're salts that get sold, and the margins on that are astronomical. They often lose money on the machine. It's sort of like the inkjet printer model. You might as well just give away the inkjet printer and charge them for the ink, right? And that solution works great when you got Office Depot all over the place and people can go out and just buy ink. It sucks when you're talking about developing countries where you have to then pay for all aspects of it and they break all the time. And so it's fundamentally about how the thing was designed from the beginning, right? So it was never going to work in that context. And the reason USAID pushes for US-made companies, of course, is because part of their goal is to spur on new markets for US companies, right? So it's just a way of funneling money through to make that happen. And that's a good thing for US business. It's not necessarily the right way to solve the problem, right? So if you want to change how that works, you fundamentally need a different incentive structure, or it's just continue to be the same. And the last bit is, you know, working a lot in Latin America, whenever you go down and you see the deals that they're closing, they're often closing deals for machines that nobody's still wanting to buy in the US at a higher cost with service contracts that are probably worse, right? And so when things become rather obsolescent here, it's like, oh, what other market could I unload it on, right? And so that creates also the wrong incentive structure. And so technology is awesome. We all love technology, but if you want to deploy it to answer a question, you got to make sure from the beginning it's planned to do that, in terms of the maintenance, right? And so I think it really fundamentally depends on the funder and who's paying for it, and really understanding what you're getting.
Well, let me follow up on that last two comments. And both of the questions from the audience have focused on issues about the deployment eventually in developing countries. The reason we were thinking about this particular topic at this particular conference is because we're in the innovation hub of the world. I mean, the Bay Area is just extraordinary with respect to technological innovation, and many people come here to try to figure out what is the magic sauce. Now, the problems that you just identified, Carlos, wouldn't be a problem if, in fact, the innovation was happening in Kampala with an eye toward the market around Kampala or in Abuja or wherever. So I wonder, what do you guys see as being the elements of the magic sauce of the Bay Area that could, in fact, be transported to other places? I mean, we recently had folks from Oxford Biosciences here trying to figure out how to make it happen more around Oxford. I'm interested in the context of this discussion, how you can make it happen more in Kampala. And I wonder if you guys have insights about how we might do more of that. I mean, Amy's obviously done quite a lot of shaking the trees to try to get innovation from developing countries, and you've done a fair bit of that. But how do you create these hubs of innovation?
I think it's a trade secret unbeknownst to us, to be honest, right? It's partly the environment and the fact that you have a critical mass of folks. I think it's partly that universities are incentivized to spin out because they can invest. I mean, Stanford gets to have 10% of a spin out from Stanford, right? So they're happy to help people spin that out, But it is happening in other places, and I fundamentally agree with you. It's probably also got to do with creating the right structure so that venture capitalists in other parts of the world who take risks can be rewarded, right? And I would say it's almost beginning to break out here. Many Silicon Valley companies are wealth transfer vehicles from the public markets onto the initial investors. And so, we hold it out as this wonderful, wonderful thing, but there are all kinds of parts of the system that are also pretty sick. And so if you think about motivating entrepreneurs to really take good ideas and find access to good capitals and build real products and real services, I'd say we used to do that really well. We kind of forgot how to do that. Some folks are still doing that, but it's no secret that what you need is hard work and folks that want to take this on and the right structure so that at the end, if you do a good investment and you do a good job, and you have a diversified portfolio, you'll make money at the end. I don't know if you guys think.
I would just add, I think that we see it starting to happen in certain countries like India and South Africa and Brazil, that there's an increasing investment by government and a lot of academia, a lot of different partners around innovation ecosystems. And I think what you have here is you have the brilliant scientists and you have that motivation to sort of generate new ideas, but you have marketplaces, right? There are those connections with venture capitalists constantly talking to these guys to see what they have and see how do you bring it into a very wealthy market like the US. What we see in a lot of countries is those links don't exist. So you have some bits and pieces that are happening. It could be happening really well, but there's also sometimes a lot of duplication. There's some confusion about roles and responsibilities, and you don't have that sort of functioning ecosystem with all the different roles sort of coming together. So one of the things we're seeing is the need to be going and investing more in those ecosystems, sort of sharing that knowledge of that whole value chain and the various kind of functional expertise that you need to help be surfacing more, letting the country surface. What are the innovations? What do they need? How do you adapt? And very importantly, how do you commercialize? Because that's the missing kind of link. It doesn't happen by itself. If you're not studying the market and you're not thinking about the full set of commercialization and economic issues around introduction, maintenance, the right inputs, the flow and distribution systems of all of this, it's not going to work.
And aggressive control of intellectual property. I would say that makes a huge difference, right? The fact that out here, the first thing the venture capitalists are going to want to know is what intellectual property do you have, what trade secrets do you have, and what are you doing to protect those, right? And that's unfortunately part of the secret sauce. If everybody knows it, then you have a competitive market, and competitive markets destroy
I think
profit.
we should go to our questioners. I see hands going up here.
Yeah. Well, thank you so much. It has been fascinating, really. I want to make a couple of comments, and I want to hear what you think about it too. So I agree completely with you. So the fact is not only one of the issues that had to be done. My name is Patty Garcia. I'm from Cayetano Heredia University from Lima, Peru. So my perspective is coming from a low middle income country that is getting better economically, but still. So, so definitely one of the issues is to try to promote hubs of innovation where we need it, definitely. And that's kind of happening, okay? But in the meantime, one of the issues that could make technology that is being done in other places, make it more useful, is to try to create those bridges with the countries. And I think universities in low middle income countries in the developing world have a role. And so not only, I think we need to create those bridges with implementers that eventually can create the bridges with authorities to do what you were saying exactly. So authorities will never know about new technology unless somebody else talks about it, okay? And there is another issue. We had done a study to try to understand what were the barriers and the opportunities for the introduction of new technologies in low middle income countries. And one of the issues, which is part of the market, but is one of those bad things in the market, are the middlemen or the distributors that really raise the prices of any type of technology and do not allow us to be able to reach that technology in our countries. So I think, and my pledge is to try, I mean, you sound like wonderful people that are trying to create new things. So what about if you use this space of CUGH, for example, to create these links with universities that could be implementers locally in their countries and then create those bridges. And the last thing is, one thing that we have seen that becomes successful is when we can ignore those middlemen and try to create ways in which companies can directly sell to governments. Some governments can do that, some governments can. But then we have certain international institutions, WHO, PAHO, UNICEF, that can, using their central procurement systems, buy big amounts and decrease the prices, and that could be one way also to get into the technology, and that will be affordable, really. So
I think we'd like to take the next two. Patty, thank you very much, and we'll have an answer to that. But can we take the next two questions, because we're supposed to end this session pretty quickly, and I think the conversation's too important.
My name's Melissa Clark. I'm an emergency physician who's worked in many sites, but I'm currently working on a project based on my work in South Sudan. And you know, I'm an emergency physician. I've never invented anything before, but I saw a problem in South Sudan, and I think I have a reasonable solution for it. And what's your advice for me as I'm working on developing a project that there's no money in it? So from a venture, like my intention is it's totally cheap so people can use it. And I'm an emergency physician. I don't know anything about production or different things like this, and I'm paying for it out of pocket, so I can't really afford an IP lawyer right now. What's your advice for someone who has an idea that seems like it might work, and I'm kind of stuck figuring out the next steps?
We're going to answer that question, but then I was just told we need to vacate the room. So,
But we can, do we have to do that, can we do that privately?
okay.
Why don't you come up and speak to the panelists, and so we'll give them back their room for the next session. I just want to thank all the panelists. Michelle actually had this idea in the beginning, so I want to thank Michelle and thank all of you for coming.